Working. Okay. Hello everyone. I'm Hugo. I'm currently working on my PhD at PUC-Rio under Roberto. And today I want to present to you a new project we've been working there. It's Titan, a new programming language, more specifically a system programming language that made for Google. I'm going to go into detail what I mean by that later. I'm proud to say I'm not working alone this. This project also involved this project are André, Fabio, Gabriel, and Hisham. Most of them, for various reasons, were lucky to also be here attending. Except Fabio, who is here in our hearts and our Git repository. Roberto has also I didn't write his name here because I didn't make it look like there's like benevolent dictator for life approval stamp, but he's been instrumental acting as advisor to both me and Gabriel, who's also a graduate student now, and he's also helped a lot in guiding the project and giving us lots of information about the guts of the Lua interpreter, because we're going to get there later. So, first of all, why are we working on this project? What are our goals? I think giving a goal at the start and never losing sight of it helps a lot. So, okay, what are we trying to do? Well, the first thing we want is we are interested in optimizing compilers and interpreters for Lua. So, why do we want to optimize our programs? If you ask this question, the first thing to come to your mind is to make our programs run faster, of course. But I think there's a better reason for that. It's because when we have an optimizer we can trust, we allow ourselves to write more beautiful codes than when we don't trust the optimizer. So what do I mean by that? There's a lot of the tricks that we do when we program, because we want to make our programs go faster, and we don't trust that if we don't do that, it won't be fast enough. Raise your hand if you ever did something like this. For example, oh, there's a global function in a global library. Oh, I'm going to cache that into a local variable. Or, oh, they would have inserted a function call. Function calls are expensive, so I'm going to do array indexing instead. Or, oh no, there's another function call, and I hate function calls, so I'm going to do a plain numeric for loop. This is the kind of thing that hopefully you want an optimizer to be handling for you. And just to clarify a little bit, with spoilers later on you see some code that looks like Lua with types in it. And if you recognize Fabio and André, they worked on typed Lua, but this is not typed Lua. And André was giving another talk and he'll go more into detail about that. And moving on. There's two main approaches to get you're writing a program in Lua and want to go fast. Well, first approach, you find a way to make the Lua VM go fast. And the example of this category is LuaJIT, which is a highly optimized alternative Lua implementation. And the other approach you can take is, well, stop using Lua, use a different language to write the parts of the program, and use the CPI to communicate with have two languages working together. Well, the first option is optimizing Lua. Well, the state of the art today when it comes to optimizing dynamic programming languages is just-in-time compilation. Just to brief remind for those who are not super familiar with the details of how this works, the way just-in-time compiler works, the original part is that writing a traditional compiler, just like GCC, it's not easy to do for a dynamic language. So what we do instead is just-in-time compilation, which is you start running your program, while it's running, you inspect the values, so look, oh, this thing here is an integer, and it's always been an integer. I'm going to guess it's going to continue being an integer in the future, and then you generate a specialized and optimized version of your program, compiled of course, based on these assumptions, oh, I think this is a continue being an integer, I'm going to generate code that assumes that it's an integer. And then you run this fast code. If it continues being an integer, then you're good. But if it's not, it's a oops. And then you have to, when you compile this code, you have to include fallbacks and wait for, oh, if your assumptions are wrong, you need to be able to rewind and go back to the basic interpreter code. This is not easy. But, and in Lua, we have LuaJIT, which is a really, really good just-in-time compiler. If you, it's one of the things that I'm most impressed by LuaJIT is that the overhead trade-off is really, really good compared to other JITs. Like many other JITs, they start really slow and only go fast later. LuaJIT is better than those. But there are some difficulties with having a just-in-time compiler implementation. First of all, writing those just-in-time compilers is a very hard, challenging engineering problem. First of all, the problem of optimizing a dynamic language is fundamentally difficult. I can go into details later in questions if you're curious. But what this means is that there's no easy task to write one of these JIT compilers. In practice, you often see LuaJIT, for example, is a decades-long project. The other JITs in the wild, for example, the JavaScript JITs you find in most browsers, there's a team of dozens of highly trained and qualified engineers working full-time with them. There's lots of still open problems on what's the best way to make a just-in-time compiler. The tooling for them is really also still an open problem, so most of these just-in-time compilers are written from scratch. They don't really reuse existing compiler infrastructure. And one of the things that comes out of this difficulty is that making changes to the language is very hard if you have a just-in-time implementation. So if you're already familiar with the Lua world, LuaJIT doesn't implement all the Lua 5.3 features. And it's really, really difficult to add those features to a JIT because of all this labor-intensive process that is writing the JIT and all the little decisions that made sense originally. Now, if you want to make a slightly different language feature, now you have to rewrite thousands and thousands of lines of code, of highly tricky code. And this is the main problem of what I'm trying to say is that this is not something that's, oh, it's hard, just put more people working on it. It's something that has an impact as well. The other less obvious problem of a just-in-time compiler is what it tries to do is that it doesn't guarantee that all your code is going to be evenly optimized. What happens is, if you have code that you throw at the just-in-time compiler and it generates efficient code and it fits all of those assumptions that the compiler likes to make, then it's going to run really fast. However, if your code doesn't fit that model that the just-in-time compiler has for what it wants your code to look like, or if you have code that's a little bit too dynamic and then falls off of the fast compiled path, it's going to be just as slow as a traditional interpreted program, or perhaps even slower, because all that fallback code of going to the compiled code and then having to fall back, there's overhead to that. So sometimes I might have a program that's the difference might be 10 times as fast or slower, and it's not obvious which, if you're going to be, if you look at a program, it's going to be a fast one or a slow one. In fact, I remember that in previous years there were presentations specifically about writing tools to help programmers underline, oh, is my code going slow on LuaJIT, and what do I have to tweak to make it go to the fast path? So this is the basic difficulty of using a just-in-time compiler approach to making dynamic language or Lua go fast. Well, that's the other way, which perhaps to say is the original one, Well, why don't you code the performance-sensitive part of a program in C? Who hasn't already heard that before, right? And the idea behind this, well, Lua wasn't made to go super fast. Why are you trying to make Lua go fast? Why don't you use a language that was built to go fast if you want to go fast? So, and this is what a bit of the basic idea behind scripting language originally. Nowadays we try to write our whole system in what looks like a scripting language, but originally the idea behind scripting really was that you had two languages working together. You had a system language that was a lower level, statically typed, compiled language that you use to write your core components. And you have a scripting language that's a more flexible, dynamically typed language that you put on top of that to glue those pieces together. And these languages, they have different goals and that drive their design. The scripting language wants to be flexible, expressive, easy to use. Meanwhile, the system language wants to be more boring, structured, and efficient. If you're on one side, you can look at the other and say, oh, that's the wrong thing. Why would you want a structured language why not be super flexible? But they have different goals. So the thing here is that instead of trying to have this one language that do everything, have two languages each working to their best and have them work together. Well, that also has problems. Well, first of all, raise your hand if you recently got a piece of Lua code that was low and you rewrote it in C. Not many people. Handful, right? Why don't we all do that? Because we all heard that, right? Well, first of all, the C API is not the easiest thing to use. I recently gave a course about Lua, and it was a 2-week course, and we covered almost everything about Lua, except the C API, because of course the C API is an advanced topic that you're not going to cover in your initial tutorials. The C API is also stack-based, and that's not a really pleasant programming model, and it doesn't look like C code. It looks like some weird hybrid C Lua code. And in practice, it's only really worth doing this if you have a large chunk of code that you want to translate to C. Because first of all, if you're going to take some existing Lua code and you're going to translate it in C, it's a whole different language. There's a lot of work to rewrite everything and get working. And then there's another issue on top of that makes it bad to rewrite just a little tiny function, and that is crossing the boundary from C to Lua has some overhead to it. It's not as so. If you're going to have a little tiny function that's called a lot from C to Lua and so forth, then it's not going to be the overhead of this call is going to be high. So you usually want either to compile a function that does a lot of work inside, or a whole module at once. And this is a problem because if you can't just go say, oh, if you want to go fast, rewrite in C, because sometimes it's a lot of work and sometimes it might even not help that much. So well, Titan is our approach to try to find a third direction in this. And Titan is a statically typed system language. Oh, I forgot to talk about this when I was talking about system languages. These names nowadays are a bit confusing. I think there's two main groups of people that use this. There's the one group as the C++ people. They see system language as language that don't have a garbage collector, and you can use it to write an operating system kernel. That's one definition of system language. But I think that in this point of view of system language as opposed to a scripting language, a more useful definition is what I see sometimes the Go community using, that they say, oh, a system language is just something that you use to write your core components, and that's something that's technically typed and more predictable, and so on. So what is Titan? Titan is the static type system language in this second definition. Focus on performance. And is designed to seamlessly interoperate with Lua and should use from there to Lua programmers. We are currently working on a proof of concept implementation for it. So the examples I'm going to give on the following slides are all liable to still changing a lot. But I think it's a good idea of what you're thinking about. So what do I want to mean by these things that I just said? Well, if you look at this, it's a little Python program for adding together all the numbers in the list. And at a first glance, it looks like Lua with types in it. And now repeat, but it's not typed Lua. And rather go more in detail about that. But the semantics of this program should behave like a subset of Lua. So you look at this, you think, oh, it should be adding together a bunch of numbers in the list, and yeah, that's what it does. And well, why statically types? Why types? Well, there's two things that main things that you gain when you have a typed language compared to a dynamically typed one. First, it's much easier to write if you compile this into efficient code. Second thing, types are useful as compiler check documentation. So sometimes when you write, when you want to write the core components of a program, it's useful to have that structure into it. The second thing is that Python was designed specifically to interoperate very well with Lua, better than C would be able to. And what do I mean by that? First, if you write a Python module and put this function into it, you can require this module from Lua without having to write all those bindings for it. Second thing, the data types that we're working here are Lua data types. So if you have an array, it's a Lua table that you're going to index like a Lua table. It's not, you don't have to be constantly converting between C data types and Lua data types. Another thing, Python was designed from the start to use the Lua garbage collector for everything. If you saw the animators talk earlier today, you know that garbage collecting between two languages can be really, really tricky. And we're purposely avoiding that by saying Lua garbage collector for everything. And finally, we carefully designed Python at all points so that calling Python from Lua and Lua from Python should be as fast as possible to not have to worry about the head of jumping from one to the other. And what do I mean when I say we designed this for performance? Well, one of the things that comes into this is that that makes it hard to optimize code is that one of the things that it's hard to just want to look at this Lua program and generate fast code into it. For example, if you raise these types and treat this like the dynamic Lua program here, things that can happen that are hard to optimize. First, if this access parameter is not a list, then when you try to index it, it's going to give an error. And the implementation needs to be able to handle that error. Similarly, if this I here is not part of the list, either if this field is not a number, then you can't not add it, or if this I is out of bounds and that returns no, that's also going to be an arithmetic error. The implementation having to deal with all these errors and all these cases, that slows it down. So one of the things that we gain by adding these types and thinking about performance is that we optimize it. Another thing that makes Python a different language, that's why we give it another name and not just Lua with types, is that you're not following exact Lua semantics, we are restricting it where it helps us go fast. So for example, in this code, right at the start, if you pass a value that's not a list into it, it's going to produce an error right there. And if you exit the I out of bounds, it's not going to return 0. It's going to give you an error right there. Because you thought, oh, this is an array, this isn't just a regular table. So since you told it that's an array, it feels free to go on and say, oh, if it's out of bounds, I'm going to give you an error. And that allows you to generate better code. Another thing that we can get when we design the language purposely for all of this is that we can add abstractions to it to help achieve our goals. For example, oh, we want fast data types. Instead of trusting on hash tables or trusting on a just-in-time compiler, looking at a hash table and behind the scenes compiling it into a more efficient representation, we can give the programming direct access to that and say, oh, here you can have a data type declaration. They say, oh, this is my data type, these are the fields of my data type. It's going to be compiled to something efficient representation for all of this. And you can have these abstract over. There's a data type, compound data type with an X field and a Y field, and it's going to work better than, and this is going to compile into something faster than a hash table. And another thing that we can get for cheap when we make a new stacking type language in the Lua family, that we can add a LuaJIT style foreign function interface into it. If you're not familiar with LuaJIT as FFI, the basic idea is that you can use some kind of syntax to declare the C function that you want to be able to call. And it automatically for you creates bindings for this function, and automatically for you, when you call this function, it converts from Lua types to C types and back and forth. And importantly for all of this, if you are inside a Titan program calling a C program, this can be compiled into an efficient C-like function call without the overhead of a C API, which is another. These are the two main reasons for why I think the LuaJIT style of FFI is appealing. It's both very convenient, little code that you have to write, but it's also really fast if you are inside that compiled code. But there are some difficulties with implementing this in when it comes to performance. There are some complications if you want to do this from the interpreter. But if you're in the type language, this comes really cheap to do. It's not a very difficult problem. So now that I talked about what are our ideas behind Titan, we have to discuss, well, how are we thinking about attacking this problem and implementing all of this? And I think there are two main things to think about when trying to figure out how you're going to implement all of this. So the first one is how do we make sure that we make our new programming language very interoperable with Lua all the time. In particular, well, if you have a Titan module, how does Lua call this code? And how do we make sure that all our objects and the Titan side of things can be accessible and collected by the Lua garbage collector? And at the same time, we want to be sure that what we're making here is going to end up being efficient, because that was our original goal, fast. And this will affect the language semantics, how we choose the behavior of the new language. This will affect what our choices are in how we generate this code, and how are we going to solve that problem of the C API that adds slowness and overhead. Well, the first thing the first bullet point there was, well, how do we make this a code in a new language and expose it to Lua? Luckily, Lua is very helpful about that. What we do is we get our Titan module, we compile it into a shared object library, just like you would do if you were coding in C. And this can be required from Lua, just like you would be able to require a C module. And the Titan functions inside that use the same calling convention as C module functions do. They receive a Lua state pointer, they return integers saying how many parameters they're returning, they push and pop things to the Lua stack, and so on. But internally, it's going to be Titan code that we compile. And so from the point of view of Lua, it's like we're calling a C module. The second thing that's the GC thing is something that we have to think all the time whenever we're creating something new in Titan. There's two main things that are involved in the garbage collector. First are the data types. If you have a data type, one of those structs that I was talking about, how can the LabLua garbage collector look inside it if LabLua doesn't know about what type it is? And secondly, how do we make the other place that we need a garbage collector is stack frames into the execution stack. Because local variables might contain values that need to be garbage collected, and we need to be able to allow the garbage collector to collect them. And something important I forgot about say. One of the things that you might have got the impression when I was talking here is that, well, why don't you just change the LabLua garbage collector to teach it about titling? Well, we don't want to do that if possible, because garbage collectors are hard, and if you can get away with not having to change the garbage collector, it would be great. And we think we can do that with some clever choices. For example, those struct data types, we could implement them as just a LabLua array, where the fields are the 1 field, and the 2 field, and the 3 field, and the names are syntactic sugar. Well, LabLua knows how to garbage collect an array, right? A LabLua table. So that solves it. After the fact, we realized that this is a bit similar to what Python does with named tuples. They solve the same problem. Oh, hash tables are slow. And for titled functions, the approach we think is likely to get good results is we use the C stack by default, and primitive values like integers and floating point numbers, they go in the C stack, so they avoid the overhead of having to be stored on the LabLua stack. But all the garbage collected things, strings, tables, closures, those have to be saved in the LabLua stack as well. Just like a C program will have to do if you write a C module that interacts with these values. These values have to be in the LabLua stack if you're coding a C module. Next thing, now that I talked about being interoperable, we also want to be fast while we're doing that. So, well, what are the things that you can do to make Python go fast? Like, this is a statically typed language, but not all statically typed languages have this goal of being fast. For example, I'm a huge functional programming fan, and Haskell wasn't originally developed to be super fast. It was developed to be very abstraction friendly and so on. No, Python on the other hand wants to be fast from day one. So what do we mean by that? First, static types, because static types can be used to compile more efficient code and generate cheaper function calls. For example, since we have the static type of the function, we know how many parameters they receive and they return. So we can avoid some of the overhead that would come with dynamic function calls. Another thing is that the semantics in Python likes to fail early if possible. So instead, if it detects that something isn't the right type it wants, it gives an error right there and doesn't delay that. And so, for example, when I gave that code that sums all the numbers, right at the top of the function, we insert a test that says, check this if this is a list of numbers. If it's not a list, it bails out immediately. And then the rest of the code we can generate assuming that we know it's going to be a list. So it throws away a lot of overhead doing that. And finally, another thing you can add is purposely add support for optimized data types, such as we can allow you to use structs instead of a hash table, and we can also allow you to use raw C data types if you want to interact with C code. Next thing, how do you generate code for doing all this? Well, the first thing is that Python codes compile to native code. It's not an interpreter, so just doing this gets a good like 10 to 20% at least, because that's usually the interpreter. The overhead of just the interpreter reading the bytecodes and dispatching them and so on. We just, for free, we get rid of this. This is not something that's usually you can just do blindly in a dynamic language, because if you try to compile the interpreter loop, it goes up into a gigantic executable. But since it's a static language, we avoid this problem. Another thing that's good about generating code for a static language is that the tuning for it is much less of an open problem than tuning for creating a just-in-time compiler. You can use existing compilers like GCC, Clang, and existing architectures such as LLVM. This is a much more reasonable problem to attack. And these are all very good, and they generate good code that you can trust. And currently our goal is to generate an ahead-of-time compiler that you feed in and then feed out some executable shared library. But it's possible in the future that perhaps we do something just-in-time-ish. But of course it wouldn't be just that kind of just-in-time compilation that needs to do dynamic runtime inspection to choose how it's going to be compiled. It's just a traditional interpreter compiler that you run at runtime. And final thing that I want to get into is how we avoid the problem of the C API not being as fast as we want. Well, first, why is the C API not super fast? The main reason about this is that the C API, if you look at it, it's actually dynamically typed. When you put a value into the Lua stack, you don't put an int or put a double. You put a Lua value that can be anything. All the stack blocks can contain anything. All the function calls are dynamic function calls that you can call with how many parameters you want. It's made to expose Lua, a dynamic language, to C. So it's not. It's really good at letting the C code interact with the dynamic side of things, but it wasn't specifically designed to allow fast access to the C library. So precisely, the operations are dynamically typed. For example, if you want to do an arithmetic operation through the C API, it's going to be that full-blown dynamic arithmetic operation that can receive any parameters and might call meta methods and so on. The C API, also for programmer friendliness, it's very thorough in doing error checking so you don't mess up and do stupid things. So it checks if there's number of, if you pass the correct, if you push the thing in the stack, and there are lots of if statements that give you a friendly error message if you do something messed up in there. And well, those are helpful, but they also add a little bit of overhead. And for example, another thing that it does is that it automatically adjusts the top of the stack, so you can use relative indices. So you can use +1 and -1 instead of having global number of things. So what's our approach, our idea to avoid this? Well, we cheat. So our basic idea is that, well, instead of using the pretty C API, we are gonna go ahead and touch the guts of the Lua interpreter. The trade-off, of course, is that this is a little bit more challenging, and this will tie each Titan version to a specific Lua minor version. But we think this is reasonable because Lua is not super large language. So an example of what I'm trying to say with all of this, currently our strategy is to compile Titan code into C code and throw it into C compiler. And this gives an idea of what the kind of optimizations that using a Titan as a statically typed language built for Lua allows us to do. So, for example, this code here is compiling a simple assignment, an array assignment. First thing, we include internal Lua headers so you can point it. Sure. This is the last slide. We can point it to the data structures inside Lua. Next thing, for example, this code, I don't expect everyone to look into it, it's just so I can remind myself. So for example, one thing that we can do is that we can have pointers pointing directly inside the LabLua stack. And another thing we can do, and in this case, we do this to save this little table in the LabLua stack so the garbage collector can see it. The next thing is, for example, since we know this is an array access, and since we know, because of the type that this I is an integer, we can generate compiled code that goes directly inside the array part of the table objects without doing a hash table access and so on. And finally, since we know that we are storing an integer in it, we can avoid a write barrier on the garbage collector in the end. So a lot of little tricks that are available if you're compiling statically. And that's basically it. I'm thankful for allowing me this space today. If you want, you can follow our work in progress on our GitHub page. And if you want to talk to me later, this is my email. Thank you.
So you mentioned for the sum function that you're doing a check on the integer array before actually doing the work.
Good question.
I didn't ask. No, you know what it is.
The approach we're taking is that instead of checking it all at once, if it's an array of integers, we check if it's an array of something, and then when you read from it, we check if it's an integer. So we delay we have to do the is an integer check, but I think that's not so costly.
So you do it in the actual.
Yes. More questions?
In regards to the directly reaching into values, have you heard of a project called Dark by Henning Dietrich, like back in 2011?
Sorry, I didn't hear very well.
There's a project called Dark, or Dog, I think you pronounced it. It's sort of a hack on top of LabLua to access the internals to avoid all that checking that you mentioned. It's sort of more maintainable than other approaches, but it's sort of like a don't use this thing, but it's still might be interesting for you, I think.
No, sure. I think that this definitely in the long run wants something that's like an official low-level API with a warning sign on top. Don't use this. Because of course, you want it to be maintainable and you want to access those internal parts, but you don't want regular programmers to be using something like this.
I was curious what you do when you're a type system, when typing calls into LabLua code, and you find out the type something.
If you're calling LabLua code, it's gonna say the type is dynamically typed, and it's not gonna check anything. That's basically it.
And something of the type dynamic can be used at any time.
Yes. Yeah, you can pass any value you want into dynamically typed locally.
And you have to like cast it back on the way back.
Yes, and on the way back, you either have to, or explicitly cast it back, or you're going to have to say, oh, this is dynamically typed and I can't do anything about it.
So just how far along the project? Like, what do you feel?
Oh, how far along we are right now? Well, we have a very small prototype for a reduced version of it. It can run. It can run programs like that one, but it doesn't have stuff like the data types and the FFI yet. And bugs as well.
More questions?
Oh,
So I'm wondering about the approach for things like iterating over lists and things like that. It seems to me that once you get to the level of
accessing a single array value like you were showing there.
Mhm.
And that's taking nearly a page of C code to do that. And then you're going to do that every time for everything in an array. That's the style people end up writing in the system language. That seems quite a bit less efficient than things that are operating at the level of an entire structure, where you say, some, and you sort of you take it up one level and operate on entire structures, and you can make one call inside there to do that whole thing at the low level.
I think the approach there is that instead of trying to do something like that, or saying this is a Lua table that I'm going to try to do a clever way to access it, I think if you want to optimize even more, you might want to create other data type for that. So you have a separate fast array data type that you can have more specialized array operations. Because some of that code has to do with things like, you have to check if it's out of bounds and so on.
Just to follow up, you might find it interesting to look at some of the history of what happened with Lisp, and people tried to start making Lisp faster.
Yeah.
It looks a little bit like what you're doing here, at the level of a useful analogy.
Yeah,
It might be useful to look at.
Mm-hmm.
Just to complement that page of code was for accessing a Lua array.
Yes.
From Titan. And not a native Titan array. A native Titan array will compile down to the same as a C array.
Right, but look, yes, but that is actually what I meant. I probably misspoke. Yes,
Yeah.
you're accessing the Lua from there.
No questions? Thank you. Very short break.